One day, we will wake up to find that the energy that powers the alarm clock came from the breeze through the trees the night before. And we will go to work that morning riding the rays of the sun. It will light our cities and power our businesses. It will warm our homes and cool our workplaces. It will reduce sources of conflict and fuel our economies. It will connect us all.
The question is, when will we get to that future? How can we go from a meme-making society to an advanced one that respects nature and lives with balance between creation and consumption of resources? The answer has been by our side for many years and is proven to be a good one: technology. But how can we get to that future again? Well, we can get to that future by improving what we already have. And how do we improve what we already have? By getting to know the basics of what we already own and use. But first, let's take coffee, because who doesn't love coffee, right? Alright, let's just get started with the presentation. Alright, let's get back to basics and the point of why you're watching this video. Computer architecture. Not this one though. Let me start by explaining what is computer architecture. So, computer architecture in engineering is a set of rules, methods that describe the functionality, organization, and implementation of a computer system. While computer architecture may include the components, it isn't quite a physical level that we refer to it. We refer to a computer architecture to something more as the insides of the computer. This is the von Neumann architecture. We're talking about the logic that lays within a computer. The von Neumann architecture, as you can see, is a simple one, but most importantly is the principal architecture that every digital modern computer has. It relies itself on having peripherals, which are inputs and output devices. The input devices serve as a way to have direct communication with the computer operating system without having to program or send electricity. We can just type and let the input devices do the rest. The output devices are the ones in charge of showing the results of what we can do, or more exactly, the ones in charge of presenting what we expect to see. The memory unit is the one in charge of storing important data for the processes, and finally, that leads to the CPU, the Central Processing Unit. We can also call the CPU the brains of the computer. Okay, no, but seriously, the CPU is where most calculations take place. In terms of computer power, the CPU is the most important element of a computer system. But that's just the core of the computer architecture. Going back to the initial von Neumann diagram, we can see the bigger parts, but the CPU and every other part has elements of its own. If we continue zooming in, we will end up with ones and zeros, so let's better explain what we have in this view. We can see the registers, the arithmetic and logic unit, and control unit. Okay, let's start with the control unit. It handles all processor control signals. It directs all input and output flow, fetches code for instructions from microprograms, and directs other units and models by providing control and timing signals. A control unit component is considered the processor brain because it issues orders to just about everything and ensures correct instruction execution. You can see it as a project manager of the CPU or the computer. It takes input from the instruction and status registers. Its rules of operation or microprogram are encoded in a programmable logic array or random logic or read-only memory. Computer control units are designed in two ways: hardwired, which is based on a fixed architecture, or microprogram control. Microprograms are stored in a special control memory and based on flowcharts. So now you know you should respect your project managers and your control units from now on. Following the von Neumann architecture, we have the ALU, or Arithmetic Logic Unit. It is used to operands and code to tell which operations to perform in input data. After the information has been processed by the ALU, it is sent to the computer's memory. So here we can see a bitwise operation, which are one or more bit patterns or binary numerals at the level of their individual bits. It is a fast, simple action directly supported by the processor and is used to manipulate values for comparisons and calculations. On simple low-cost processors, typically bitwise operations are substantially faster, several times faster than multiplication and significantly faster than addition or division. Now, registers. A register is one of a small set of data holding places that are part of a computer processor, and it is usually a quickly accessible location. A register may hold a computer instruction or addresses or any kind of data, such as a bit, sequence, or individual characters. Some instructions specify registers as a part of the instruction. For example, an instruction may specify that the contents of two defined registers be added together and then placed in a specified register. A register must be large enough to hold an instruction. For example, in a 32-bit instruction computer, a register must be 32 bits in length. So, that leaves the question, what kind of registers do we have? So we have data registers, address registers, general purpose ones, which can be data and addresses. We have status values, floating points, constants, special purpose, which could be program states, and also we have registers related to fetching information from RAM, which are the memory buffer, the memory data register, and the memory address register. Alright, now the important stuff. CADs. Nah, just kidding. It's just so you don't get bored. Let me continue with the presentation. We're almost done. Well, now let's talk about peripherals, especially memory. Memory refers to the computer hardware devices used to store information for immediate use in a computer. It is synonymous with the term primary storage. Computer memory operates at a high speed, for example, random access memory, as a distinction from storage that provides a slow to access program and data storage but offers higher capacities. If needed, contents of the computer memory can be transferred to the secondary storage through a memory management technique called virtual memory. Now, cache. Cache is a hardware and a software component that stores data, so future requests for that data can be served faster. The data stored in a cache might be the result of an earlier computation or the duplicate of data stored elsewhere. A cache hit occurs when a requested data can be found in a cache, while a cache miss occurs when it cannot. Cache hits are served by reading data from cache, which is faster than recomputing a result or reading from a slower data stored. Thus, the more requests can be served from the cache, the faster the system performs. However, you don't want to keep your cache for 1,000 years. You know, that would be not good for you. Not good. Now, input and output. In computing, an input device is a peripheral used to provide data and control signals to an information processing system such as a computer or information appliance. An output device is any piece of computer hardware item used to communicate the results of data processing carried out, which converts the electronically generated information, ones and zeros, into human-readable form. So, the question is, why is all of this important? It is important just so we know what can be improved in the future generations of computers. As you may have seen, the control unit just takes care of simple processing units. So as we progress, we will be able to do more and more complicated operations. They also help you understand what the compiler is talking about when it tells you invalid address exception or stack overflow error, and you know that happens. Also, it helps you get a better overall idea of what is going on the insides of a computer when you run your programs. Finally, let's take a look at modern architectures. A NOR bridge or host bridge is one of two chips in the CoreLogix chipset architecture on a PC motherboard, the other being the South bridge. Unlike the South bridge, NOR bridge is connected directly to the CPU via the frontside bus and is responsible for tasks that require the highest performance. The NOR bridge is usually paired with a South bridge, also known as input-output controller. In systems where they are included, these two chips manage to communicate between the CPU and other parts of the motherboard, and constitute the logic chipset of the PC motherboard. Separating the different functions into the CPU NOR bridge and the South bridge chips was due to the difficulty of integrating all components onto a single chip. As CPU speeds increased over time, a bottleneck eventually emerged between the processor and the motherboard, due to the limitation caused by data transmission between the CPU and its board chipset. Modern Intel Core processors have the NOR bridge integrated on the CPU die integrated circuit, where it is known as the Uncore or system agent. And since there's not much time left, let me say thank you for your attention.